Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so we're happy to have David Stoyer here from Princeton. Many of you know David since he was an intern with us last summer. I think most of you know him. You certainly know his collaborator on this work. So he's going to be talking about the unique games conjecture and graph expansion.
Okay. Thanks. So this a good part of this work was actually done while I was an intern here last summer. Okay, so we give a roadmap of the talk. So first I will be some introduction and will sort of motivate the problems that we are looking at, and then I will sort of more precisely define or say what we are proving, and I will give you some idea about the proof. Okay. So let's start with a great example of MaxCut. So MaxCut is a combinatorial optimization problem, and a very basic combinatorial optimization problem. And it asks you to partition the vertices of a graph into two parts, so as to maximize the number of edges that go between the two parts. And so one way to let's see. There's one way to think about it is that these edges indicate conflicts between your vertices, and you try to cluster them into two parts so as to minimize the number of conflicts inside a cluster. Okay. Okay, and so you know, besides this being a very basic and simple question, it actually comes up in practical applications. So one sort of random application is that this corporate association for internet data analysis at UCSD, they use a very similar problem to analyze the business relationships between autonomous systems in the internet. Okay, so it's sort of surprising, but and then so actually they contacted us and wanted to know if how to implement our algorithms. And okay, so we really want to solve this problem, but yeah, unfortunately you can't solve it exactly. So it's NP hard if you want to find the optimal solution. And so what we want to do instead, we want to find approximate solutions. And okay, so the trivial approximation that you can achieve is just by assigning the nodes randomly left or right, and then in expectation half of the edges will go across the cut. So that's the trivial approximation. And the first non-trivial approximation, and still the best approximation, was by Givens and Williamson in 95. And so remarkable thing about this is that they used a semidefinite programming relaxation to achieve this approximation, and this I will call this relaxation the basic SDP. Okay, and so just in case you know about this and you want a reminder, so what you try to do is you embed the vertices of the graph onto a sphere, and you try to maximize the total squared length of the edges in this embedding, and that will be the solution to this relaxed problem, and then you round it using a random hyperplane, and that achieves this non-trivial approximation. The factor is something like 0.878. Okay, and MaxCut is not the only problem for which this approach works. So this basic SDP, you can define it for a great variety of different problems, and almost always it gives the best known approximation guarantee, and typically it even does better than any non-SDP methods. Okay, so this sort of a great algorithmic tool, and the question is if we can we beat somehow this approximation guarantee of the basic SDP for MaxCut. Okay. And the answer is no, if you assume the Unique Games Conjecture. This was a result of two works by Khot, Kindler, Mossel, and O'Donnell, by Mossel, O'Donnell, and Oleshkewicz, 2005. So what is this Unique Games Conjecture? So it was introduced by Khot in 2002, and it roughly says, so for now it will be enough, that this unique games, the value of these unique games is NP hard to approximate. And it's sort of important, in which sense we want to approximate the value. But for now, just take it as that. And so it's sort of a kind of a bad name. So it's not really related to game theory in any case. In case you're wondering. Okay. And again, MaxCut is sort of is not an exception, but it's actually by now there's a very impressive list of problems where we know that the basic STP is optimal if the Unique Games Conjecture is true. And sort of this list contains really some of the most fundamental combinatorial optimization problems that we care about. Okay. And so in most cases, this R is Raghavendra, Prasad Raghavendra.
Three set, for example, is I don't see on the list. So
Max 3 set it would be here. I mean, so here I just sort of gave some examples of the classes.
Oh, I see. So all Max K set is in.
Yeah. So what's remarkable about this is that it's not just known for specific problems, but for whole classes of problems. Okay. And so this is like a very satisfying situation. So you have this kind of cool tool, this basic STP that gives you a good approximation, and on the other hand, you can't do better, assuming the Unique Games Conjecture. Okay. So if you just shorten this list, so that's the basic message of these results, that the basic is optimal for a lot of these fundamental optimization problems. Okay. And so everything is fine with it, except there's one problem, and so the problem is that we don't know if the Unique Games Conjecture is true. And that alone wouldn't be a problem, because for a lot of complexity conjectures we don't know if it's true. We don't know if P is different from NP. But
you were mentioning vertex coupling. Does the STP give any?
No. I mean, so this basic STP is better than the LP. I mean, so vertex coupling is one example where the STP is not strictly better than other methods. Yeah, some greedy algorithm or some simple algorithm that's better. That's as good as. Right, and so it's not just that we don't know if it's true or not, but we don't even know if something non-trivial happens if it's false, and that's very different from the P versus NP situation, where we know that if there's an efficient algorithm for 3 set, then there's actually an efficient algorithm for everything for every problem in NP, and this is very problematic in this picture. And sort of people are of course aware of that, and so what was tried is to make this situation sort of more desirable by saying that the Unique Games Conjecture is implied by this natural conjecture about MaxCut. So you want to say that Unique Games Conjecture is true if the basic STP is indeed the optimal algorithm for MaxCut. So and this would sort of lead to some kind of win-win situation, that either the Unique Games Conjecture is true, and then we settle all the approximation complexity of all these problems, or if the Unique Games Conjecture is not true, then this conjecture has to be false, and so there has to be a better algorithm for MaxCut, which is also great.
But it wouldn't give you that
algorithm. Most likely would. It sort of depends on how you exactly prove this implication. But I mean, the usual way to prove this is by some reduction, and then it would sort of tell you.
And then it would give you. Okay.
Right. Yeah. So that's important. So all these implications are proven by some reductions, from so in this case from Unique Games to these problems, and here in this case you want a reduction from MaxCut to Unique Games, and this okay. So that's why I call these reverse reductions. So we know reductions from Unique Games to other problems, and now we want a reduction from some other problem to Unique Games. Thanks.
So are there other situations? What if factoring were easy?
Yeah, it would also be good. We don't. I mean,
we don't know much consequences of.
You're saying that? That's true. I mean, most likely it's easy. Or I mean, for quantum
Except that we're all messed
No,
up
no,
in
even
terms
that's
of
not
our credit
much.
cards. But,
No, but I mean complexity-wise, right? We had,
Um,
I mean, except some sort of hardness of, I mean, okay, if factoring would be easy, some approximations would be difficult, but it's not that if factoring were easy, we would have a slew of problems which we suddenly could do.
That's right. Yeah. I guess. I didn't think about factoring. I mean, so I guess the issue is that some of factoring, there's sort of not clear what it's related to. I guess there's a discrete log or so. There's some conjectured relationship between them, but yeah. Okay. So and then so there was an approach for this, and so this parallel repetition is a natural way to take a maxcut instance and get a Unique Games instance. And this was suggested by Feige, Kindler, and O'Donnell in 2007 to sort of that this reduction could work for reducing maxcut to Unique Games. But the problem is that this reduction, it's known that it doesn't work. So Ran-Ras found a counterexample, so an instance for maxcut where somehow the reduction behaves different than you would want it to behave. And then some follow-up work with my co-authors and I showed that it's sort of it's actually more the rule than an exception in this instance. So in some sense, we show that all the interesting instances of maxcut, if you apply this reduction doesn't work as you like. Or in other words, we show that these Unique Games instances that come out of this reduction, by taking some maxcut instance, applying this parallel repetition. If you look at this Unique Games instance, then it's actually easy to solve these instances. Okay. Okay.
What's the property that makes them easy?
So this parallel repetition is some kind of product instance product, and so the SCP solution will be tensor products of vectors, and that allows you to round them better than other arbitrary SCP solutions. But it's sort of I mean there's sort of some tricks involved. Okay, right. So okay, so this is the situation. So, but maybe we were just unlucky that we tried here maxcut. Maybe we should try a different problem to reduce from. And okay, it's what we're doing in this. Well, that's what I will talk about. So we will take here a problem called small set expansion, and so we take the same conjecture, and then we will show that it implies the Unique Games conjecture. And then we have this sort of win-win situation that either the Unique Games conjecture is true and we get all these implications, or if the Unique Games conjecture is false, so meaning that there's an algorithm for Unique Games, then it implies that there's a better algorithm, that there's an approximation algorithm for the small set expansion problem that is much better than the basic SCP.
Is small set expansion here, is this something very specific to this particular problem, or are the techniques broad enough to apply it to various different...
It's sort of specific to small set expansion, yeah. Okay, and so the selling point of this result is that it's the first reduction from a natural optimization problem, the small set expansion, to Unique Games. So previously all the reductions were the other way, and this is the first reduction in this direction. Linear size.
Linear size.
Yeah, but going to zero, I mean the fraction.
So
0.00001.
So you
yeah.
describe the problem, right?
Yeah. That's the second bullet in the roadmap. Okay, but I think that's actually what happens now. So now we will talk about this. Okay, so what is graph expansion? So we have a graph, and let's assume it's D-regular, so all the vertices have D neighbors. And we are interested in measuring how well parts of the graphs are connected to the rest of the graph. So we have some part here, and the way we measure this connectedness is by the expansion. So we look at the number of edges that leave the set and divide by the degree times the size of the set. And then so notice that this is the number between 0 and 1, just because they at most d times size of s edges that sort of are involved in this set. And it's a number between 0 and 1, so most likely you can think of it as a probability, and it's the probability that that you leave S if you pick a random vertex inside of S and then pick a random neighbor. Chance that you get outside of S, that's the expansion. Okay, so it's expansion. And typically what you look at is the smallest expansion of a set in the graph that has volume less than half, and volume will here mean the fractional size of the set. So half of the vertices. At most it should contain half of the vertices, and it's just because somehow there's always two ways of looking at the sets, at the cuts, either from this side or from this side, and so this makes sure that you look at it from the smaller set. Okay. Then sort of related notion, generalization, not as coarse a definition, is that you look at sets, only sets that have volume delta, so the only delta fraction of the size of the graph. Okay, and so this notion of expansion and this expansion of a graph and expansion profile of the graph, it's very important for lots of things. It comes up in many contexts. So zero randomness, group theory, some online routing, and also Markov chains. And in particular for Markov chains, it's sort of important to have to look at these things sometimes.
Now you only consider regular graphs, or could D be the average?
No, so if it's not a regular graph, then you would put here the number of edges that the sum of the degrees in the set.
Oh, I see.
Yeah. So yeah.
It might make sense to define the volume differently also.
Yeah, volume will then be the fraction of the degrees inside this. Sorry. Okay. Now, what's the conjecture? This small set expansion conjecture is that okay, some quantifiers involved. So for every epsilon greater than 0, there should be some delta, so that it is NP hard to distinguish between the case that all small sets, small meaning volume roughly delta, there exists between the case that there exists a set that has small expansion, and the case that all sets of this size of this volume have a large expansion.
Will you make the Twitter a little bit more precise?
Let's say up to a factor of 10 or so.
Okay.
So you consider epsilon and delta here to be constants, or
Yeah.
they can depend on the size of the graph?
No. So I mean for every epsilon and delta you have sort of this promise problem,
Oh,
and
epsilon is just
it's
fixed.
constant. Yeah.
So and the promise process says within a factor of 10?
Here in the volume, let's give it a slack of 10. It's sort of a bit. I mean, it's probably not necessary to put this here. So we ideally would like, just saying the volume should be smaller than delta, but there will be some problems if you do that.
Typically, in the yes case, you would want it to be for a slightly small set, and in no case it should hold for even larger sets. Is that why you have the approximation?
So you can make it works if you have here the same kind of approximation if you have a factor of 10, but in some sense it's more. I mean you sort of can on some level what you're saying would allow you to sort of make this a bit more precise, everything. Yeah.
So do I understand right that you prove this is equivalent to the Unique Games Conjecture?
Okay, so that's
It implies, but not equivalent.
It implies, yeah. So it's.
But this doesn't fall under one of the ones where Unique Games Conjecture implies.
Yeah, right. It's one of the few problems where we actually don't know how to.
So you're also doing a separate, so you're also separating, if the Unique Games Conjecture is not true, then you're also separating this from those other problems.
No, I mean these other problems could then be easy, right? I mean.
They could all be
yeah, of
easy.
course they could. Okay, fine.
So there are some implications of unique games to expansion.
So the issue is that some of these, so these reductions that, so you have to assume a little. Yeah, okay. What we show is that if you make a slightly more a stronger conjecture than unique games, where you add an additional assumption on how the graph, the constraint graph looks like, then you can reduce unique games, this slightly stronger version of unique games to this conjecture.
So then they are equivalent,
If you
No, the issue is that so we don't know if this conjecture implies a slightly stronger version of the conjecture.
maybe you can find out a little bit.
So yeah, so I mean it's also so this is fairly recent work, so I'm sure that at some point these things will be resolved. Okay.
You had a question, Henry?
Okay, so just to mention, so one way to approximate expansion, especially at this sort of constant scale, is Giger's inequality, and so it talks about the case really where delta is 1/2. And there, I mean, it would allow you to distinguish between the cases, right? Because there's only this epsilon versus square root epsilon kind of a gap. So you could distinguish between close to 0 and close to 1. But it would be just the eigen, or would just compute the eigenvalue gap of the graph. And then Giger inequality would tell you that the eigenvalue gap allows you to distinguish between these cases. If the eigenvalue gap is close to 1, then you're in this case. If the eigenvalue gap is close to 0, it's in this case. Okay, and but on the other hand, somehow there's no good generalization of Giger's inequality for this problem. So we know that this basic STP and certain STP hierarchies they cannot. I mean,
So it goes to 0. You mean goes to 0 with n?
No. In sort of in this case,
Okay,
you
so
can make
still
it arbitrarily
constant.
small. Yeah.
Still comes. Interesting.
Okay. And
you're saying you can show the implication rather than you can show the top line, and that implies the second line?
oh no, sorry. Yeah, we can show this line.
Okay, so you can show that.
Yeah, we can show both. Okay.
Okay.
So
Sorry.
so what does mean no generalization? I mean,
No, I mean, so the natural generalization of Giger's inequality would be, would be to look at this basic STP or maybe STP hierarchies and then see what kind of approximation they achieve for a small set expansion. So because I mean, Giger's inequality sort of you can think of it as in some sense it's weaker than the basic STP for expansion. So you could look at the basic STP for the expansion problem at delta equals to 1/2. That would then as if so Giger would show that you could have a good approximation in this case, and
So what do you consider to be the basic STP here, with triangle?
no, without triangle quantities.
Then it's exactly Giger's.
Yeah, I mean it depends a little bit on what you look at. Yeah. That's right. So if you want delta equals 1/2, you would look at the balanced separator version sort of.
Mm-hmm.
Yeah. Okay. Right. So, okay. Now we'll talk about unique games. Okay. So what is a unique game? So it's okay. So usually I define unique games in terms of graphs, but because we have graphs in the other problems, I won't say graph here. So we have a universe of size n, and then we have for every point in that universe we have a label set L of A. Okay, and these label sets are going to have the same size. And then so in addition to these label sets, we have a distribution over triples, sort of 2 points in the universe, and a bijection between the label sets of the 2 points.
wait, are A subset of the universe?
No, A is a point in the universe. Okay, so the notation will become clearer in the later part. So A are points in the capital A, sorry, points in the universe. So or vertices in this unique games graph. Okay.
And L of A is sort of isomorphic to L of B.
Yeah, same size. Yeah. So you can. So I mean, it will be convenient for us to have sort of different sets in the reduction. Will all of this is the same size, and just by renaming, you could make them all the same set. But, yeah. So okay, and now what's the game? So look at the following process. So you have 3 parties, a referee and 2 players. And what the referee does, he samples secretly such a triple from the distribution. So all participants know exactly, know everything that's going on here. So the referee secretly samples a triple from the distribution, and he gives sort of the first coordinate of the triple to player 1, second coordinate to player 2, and but they can't communicate. So they just the only thing they see is this this thing, and player 2 only sees B. And then they are supposed to choose an element in the label set of the thing that they receive, and then send it back to the referee. And what the referee does, he checks if the elements that he received from the players satisfy this bijection.
You said this before, that this boils down to saying that all the points have the same label set?
So I mean the points having the same labels. Sorry.
What's the difference between having this bijection and saying that all the points have the same label set?
Oh, the bijections, they could be. I mean, so.
If you follow a loop, you may not get back to where you started.
Yeah. So somehow, I mean, okay, so the bijections might not be consistent in this case, in this sense.
So the players know everything except for the choice.
Yeah, except for the secretly sampled. And of course, the optimal strategy for the players, it would be some optimization problems, So they would try to satisfy as many of these things. Label they pick for the label they pick for capital A would be so that it maximizes the number of satisfied things. Okay. So there's no communication between the players here, and okay, now the value of the.
So is this why Subhash called it a game?
Yeah.
See, okay.
So actually
I don't think he's the first one.
It's called Unique Game by Feige and Loas.
Oh,
Yeah.
Was it?
But also, I mean. But
You
yeah.
have to blame somebody more.
More senior, okay.
And did they have already this formulation or not?
Yeah, this formulation.
Let's see.
It is a game. It's not a zero-sum game.
It's a cooperative game.
Yeah.
Okay. And the value of the game will be just the maximum success probability over all the strategies that you can have. Okay. Now the Unique Games Conjecture. So the quantifiers are similar, and that's sort of what helps us to show this implication. So so what is the conjecture? So it says for every epsilon there should be some large Q, so that if you have a unique game where all the label sets have size equal to Q, say, then it's hard to distinguish between the case that the value is close to 1 or close to 0. And closeness to 1 is measured by this epsilon. Okay, so the quantifiers are sort of similar to the case in the small set conjecture, small set expansion conjecture. And what? Yeah, no trigger. And so what we show is that the previous conjecture implies this conjecture.
Will you get some relationship on the for all on the exist? How big Q as a function of epsilon is?
Yes. So Q will be pretty much 1 over delta. I mean, so so it's not. I mean, yeah. So we don't see what's the relation between Q and epsilon here, but we sort of see what's in the reduction, the relation between the. Yeah. Okay. Okay. Right now. So what's the time actually? So this. Sorry.
Time is 12:20.
Okay. Yeah, that's good.
Somebody's looking at it?
Yeah.
So okay. So what's the reduction? So we want to reduce small set expansion to unique games. So we have a graph. So we have an instance of this small set expansion problem. So we have a graph, and we want to find a non-expanding set that has value volume delta. And so this is the instance, and now we want to create a unique games instance out of this instance. Okay. Now how do we do that? So so what does the referee sample? So he samples first. He samples R random edges in the graph, and R is equal to 1 over delta. Okay.
So M is the set of edges?
M is the set of edges, yes. And with high probability, because this is a constant and the graph is huge and regular, these will be disjoint edges, matching. That's why it's called M. And then he will sort of call one set. I mean, we'll then take half of each set and call it A, and half of the other half. Half of each edge and call it A, and take the other half of each edge and call it B.
Again, randomly?
Yeah, you can make it. Yeah, randomly is good. And then
assume these edges have disjoint endpoints. They might not.
With high probability.
yeah, I mean they will with high probability. Yeah. I mean, so this is really, it's not precisely the reduction that we use. Okay, it doesn't really work that way, but that's sort of the intuition. Okay, so then he sends A and B to the players, and they are just supposed to pick a vertex out of the set that they receive. Okay, so one of these points, and what the referee checks is that the vertices that were picked by the players corresponds to the same edge, corresponds to one of the edges that was chosen initially. Okay, so now let's see why sort of what's the intuition, and so the way we see that is.
But even though you're implicitly getting some kind of cut, it's not really a cut, but you obviously can't take this to a result on the max cut because that's false, right? Okay.
No, yeah. I mean, so what we will do next is we will say that if there's a small set that doesn't expand inside the graph, then we can find a good strategy for this game. Okay. So this is just okay, and so this is sort of one direction of the reduction, and we want to say that if there exists a good strategy in the game, then there is a small set that doesn't expand. So I think that's what you meant. And the harder direction will be this direction, that to show that the strategy implies a small set that doesn't expand. Okay, so let's see why the easier direction is true, and so that will also make sense why the reduction looks like that, or shows. Okay. So suppose this is a set that doesn't expand, and so what's the strategy in this case? So actually, I won't give you like a complete a real strategy. I will only give you a strategy that answers a constant fraction of the sort of where the players pick a label for a constant fraction of the possible sets, and it turns out that that doesn't really change the problem. So it's easy to say that, easy to see that, or easy to prove that sort of these partial assignments or these sort of partial strategies, computing those is as hard as or it's not easier than computing real strategies. Okay, so what they do is they look at the set that they get and compute its intersection with a small set. If it's exactly 1, then they will pick that vertex. If it's larger than 1, or if no of the intersection is empty, then they will refuse to answer, and they will tell the referee that they refuse to answer. And they win either if they both refuse to answer, or if they correctly answer, or if they satisfy this constraint. In both cases, they win.
Why can't they just always refuse?
So that's the constraint. So they have to answer a constant fraction of the queries. No.
No, they win.
They win if they. But they have to. They have to answer.
Always refuse to answer.
Yeah. They have to answer on a constant fraction of say it will be something like 1 over e or something.
Right. So you should refuse to answer as much as you're allowed to.
Yeah. Whenever you are unsure about.
Right.
Yeah. And okay, and we are unsure if the intersection is not equal to 1. Okay. So now, okay, why is that a good?
How often is this intersection just 1?
Yeah. So it's so because the set size 1 over delta. So the set size delta. No. So the intersection being 1 is just a property of the size of. It must be a property of the size of the set. So because A will be it will be just R random vertices because the graph is regular.
Yeah.
And the chance that one of these vertices falls inside of S is delta, and you have you have 1 over delta of them. So in expectation, one of them falls inside, and you can compute that there's a good probability that exactly one of them will fall inside the set S.
What is good? Fixed constant, or is it very close to 1?
It's a fixed constant, something like it's 1 over E or 1 minus 1 over E, one of these things. Okay. So now let's condition on this event that happens. Okay, so we sample A and condition on the event that exactly one of the things is inside. And now this point that will be inside of S, it will be a random point in S. Okay, and now let's look at the neighbor that the referee sampled for this point. So the point is that because of the expansion, it will be inside of S it will also be inside of S with probability 1 minus epsilon. And just because the probability that you go outside of S will be epsilon. So that's what I wrote here. If you condition that on the event that exactly one of the vertices of A falls inside of S, then the other half of of the edge of A is in S with probability 1 minus epsilon. Okay, and so that means that also player 2 will pick that vertex. So
how do we know it's unique?
yeah. So there you have to compute that, but it turns out that doesn't influence. Yeah. So right. You have to also to show that none of the other vertices of B falls inside of S, but that will be true.
Checking that the big set A intersect S, the size of the intersection is 1 would not do, right? You have to do your method. Pick A if this will intersect. I mean, it's more natural to think that you would check whether the set A intersects S. There's only one element, then pick this element.
Yes.
But you take a different approach, right?
No, I mean this is just to say that. I mean, so that's what the players do. The players just look at the intersection. If it's exactly one, they pick.
Okay.
So they're not clever, yeah.
Okay.
But that's sort of to analyze what's the chance that they will satisfy this relation.
Wait, did you tell us what player B2 does?
Player B does the same. Sorry.
Oh, I see.
And so they're saying no.
I mean, yeah. So they're saying you refuse to answer for a constant fraction, and but they answer also answer on a constant fraction.
So do they use the same set S?
Yeah, they use the same set S. So that's the set S that allows them to coordinate the answers. That's what happens.
So is it correct that a slight variation that would also work would be for A and B to refuse unless both of the points are in the set? Unique in the set?
No, so the issue is that he has to decide which what to pick. Just looking at his side of the set. So the player 1 doesn't see B, so he can't.
Player 1 doesn't see B, but he knows the point that's at the other end of the edge.
No, he doesn't. There are D neighbors for that, for the small a, D possible neighbors. He wouldn't know what.
Doesn't know the edge.
Because he doesn't know the set B.
Yeah, he doesn't know the set B. Yeah. I mean, if he would know the set B, then they could, of course, answer always correctly. Okay, so
that still doesn't determine the edges uniquely, right? Even if you know B. You could take any matching between A and B.
But we said there is a unique.
Sorry, what's the question? Right.
If he doesn't know M, then I mean there might be several ways to match A and B.
There might be several. Yeah, right. I mean, the referee knows M, right? The referee does exactly this.
Yeah.
So right. I mean, but I mean, what you're saying. I mean, that will be very unlikely that if you pick a random matching and then there will be another way to match it.
Yes, because the graph is sparse.
Or I mean, let's see.
D is fixed, yeah.
The sets are small and the degree is small. So.
Right.
I mean, and independent of that, it wouldn't change, the way they pick the labels. I mean, so. Yeah. Okay, so. Okay, so that shows that somehow they can win with probability roughly 1 minus epsilon this partial game. Okay, so now the trickier part is to show that if you have a strategy for this game, and then there will be a small non-expanding set. Okay, so we assume that there's a strategy, and let's assume that it's actually a total strategy. So proper strategy. It picks. So the players pick. They don't refuse to answer. I mean, it's at this point it's not justified to do that, but it will. It won't change a thing, and will just make some things, some technical stupid little things easier. Okay, and then so another thing is that using some standard argument, you can show that the best way for the players to play is that they actually follow the same strategy. We saw in the completeness case, that's what they did, right? They chose the same strategy, and in general, that's also the best to do. Okay, so now it's just the strategy just picks one vertex, sort of picks a representative for every set of R vertices. That's what the strategy does. Okay. Now we want to create a small set of vertices in the graph. Okay, and what we do is we will transform the strategy into a distribution over sets at first, and then we will analyze this distribution and then argue that and sort of use properties of the distribution to argue that there has to exist a good set. Okay, so the way you will sample this distribution is as follows. So you first sample R minus 1 vertices and we call the set U at random. And now the set S that you output will be, it consists of all vertices X that the players would pick if you would give them the set U plus X. Okay, so you you fix R minus 1 vertices, and then you sort of look at you look at the possible things for the remaining vertices, and you put it into S whenever this guy gets picked by the strategy. Yeah, I mean we assume that they follow the same strategy. So yeah.
Okay, so.
Yeah. So for every set of size R, they will pick one vertex, and so if
okay.
in this U plus X will be a set of size R because U has R minus 1 vertices, and
so each time.
So this S is going to be a candidate small expansion set.
yes. So
You also can assume fairly deterministic
right. Both of them. You can assume the strategies are deterministic, but I mean there will still be distribution over sets.
So he means union. So he takes whatever he picks R minus 1 vertices. He calls that U. And now he adds X to it and asks, did I get A?
If I asked a U plus X,
Right.
would I get X?
When I get
Yeah.
it.
Yeah, we're missing so yeah with this. Yeah.
And he does that R different times.
This gives a random variable.
No. So X. He will look at all possible vertices in the graph. So we'll do this n times. And okay.
So this is a sort of a distribution that's producing a random variable called S, and
Yes.
that's your candidate small expansion set, and you're going to prove either with high probability or positive
Right.
probability.
I
Something
mean actually, so you prove. Let's see what. So let's look at this distribution over sets. Now you can prove something like the following two things. I mean, so it's actually not quite true, but I mean, so let's assume we can prove the following things about the distributions. Okay, so the first thing is actually something that is really true, that you can even verify it. So so the expected volume of the set S that produced by the distribution will be like you want it to be. It will be delta. That's what you're shooting for. And so this probably is not quite true, but sort of a trick to make it true. so if you look at the expected number of edges leaving S, divided by the expected number of, expectation of D times the size of S, that's small. And in some sense, that's, sorry?
Wait, so expected E of times S is just delta times N times D.
Yeah, right. That's true. But so I'm just writing this because it looks similar to the definition of expansion, right? And just the difference is that the expectation sort of both, so you're told that the number of edges leaving S is on average only epsilon times the the size of D times the size of S. So that's great. So it should somehow it indicates that. So let's just assume we have such a distribution, okay, over sets, and so does it mean that we are done, right? So that's
the expected number of edges leaving is so small is because the strategy is going to succeed with very high probability.
Yeah, right. So you can relate the number of edges leaving S to the sort of cases where the players lose, and it will be sort of exactly the same.
And why is it succeeding with such high probability?
No. So that's just what we assume. Yeah.
Now, what you're going to do about concentration?
Yeah. So that's exactly the issue.
That was very helpful.
Yes. So that's exactly the issue. So these two things, they don't imply that we are done. And the issue is just that the distribution of the volume of S might not be concentrated around its expectation. And then so one example, one case would be that with probability 1 over R, the volume is roughly 1. And if it's, let's say it's equal to 1, then no of the edges will go outside because it's the whole graph. And with the remaining probability, it's just an empty set. And then so this is sort of completely meaningless in some sense. Okay.
That can happen for some graphs.
It can't be that bad. So you can imagine that there's like a strategy where so let's actually just see why the volume of S is an expectation 1 over R. Okay. So let's so suppose we generate S in this distribution. Let's just check why the volume is 1 over R. So the volume of S, you can think of it as the chance that a random vertex from the graph falls inside of S. Mm-hmm. That's the volume of S. And now so if it falls inside of S if the players pick it, if you give it U plus X. Okay, so it means that we sample U at random and we sample X at random. And we ask what's the chance that the players pick X in U plus X. Okay. And now U plus X, it's just R random vertices. And the point is that X is a random vertex inside that set. And because the players can pick only, if you fix U plus X, they can only pick one of these guys. But X will be a random point inside of U plus X. So the chance that they will pick X is actually is 1 over R. So it's it's.
So is this problem the reason the players need to refuse occasionally?
No. So in this case, we're sort of assuming that they don't refuse at all. Even. It will only make our life easier if you assume that in this case. So so it's sort of like some simple probability calculation that this is delta, but so we don't have concentration. And then there are sort of also ways to construct strategies where you don't have concentration of this set. Mm-hmm. We have with some constant probability, it's much larger than 1 over R.
So you've got to now modify your
Yes.
strategy to ensure that it is concentrated.
Yes. So what we actually will do, we will modify the reduction. Okay. And the way we modify the reduction is the referees will add noise to the sets A and B before they send it to the players. And so by noise, I mean that they add epsilon R random vertices to the set. Okay, now the sets are slightly bigger, and so you have, in principle, I would have to check that the completeness, the other direction, still works out, but you can trust me on that. So now let's the revise strategy, and now we will be able to generate this distribution of sets in a slightly different way. So we will we'll pick r minus 1 random vertices as before. Then we'll pick some threshold t, and it's actually, I mean, for other reasons it's somewhat important from which distribution you choose it. But so if you just want to argue about the concentration, it won't be important which distribution we choose. Then this t will be some number between some constant number. That's we can even think of it as being half for now. And then what we will do, we will look at we will for every vertex x, we will look at u plus x, and then we will add noise and see what's the probability, over the noise that x gets picked. Okay.
And so what does noise mean? The same.
The noise that was added
yes,
by the referee.
No, but it's different.
No, it's the same. It's epsilon r random vertices.
Same constant.
So this is now a set of size 1 plus epsilon.
Is it two different samples from the same distribution, or is it the noise?
So here
It's the noise they actually got, right? Is this the noise A actually got?
I mean, so this is like so this is not related to the game. The game just defines, just specifies what's the value of the strategy.
Oh, I see.
So this is we do that completely, different. So that's what we do in private. We are given the strategy that for every set of size r we get some, and then we go home and try to come up with this, and so we look at what happens if I take u plus x, add random noise. What's the chance that x gets picked? If this probability is larger than half, then we will include x in the set. Okay. And now you can show that actually, even if you fix u and t, the set S can't be too large. And the intuition for that is that so even if you fix u and t, the players, they won't be able to distinguish the vertex x and the noise that you add to it. Okay. So okay, so let's see. So okay. So let's try to verify that. So suppose we let's fix u and t, and by Markov, the number of things where the probability is larger than half is at most. So if you take the expectation of that probability over x. Okay, so we can estimate the volume of S by the expectation of these probabilities. Okay, that will be some way to upper bound the size of S. So we take expectation over x of this probability. Okay. So now let's see. So what do we have? So we take, and now the point is that in this probability we average over the noise. So now we have x. We choose x at random. We choose the noise at random, and we ask what's the chance that that x gets picked in the set u plus x plus noise. And because x and noise, they both are completely random. So so in some sense x will be like a random point inside the noise. And I mean, the best thing that the players can do is that they can pick one of the noise vertices. But that will be x with probability only 1 over the number of noise vertices. Okay. The number of noise vertices is roughly delta. I mean, yeah, so
Choose too many noise vertices.
Is this epsilon the same as that epsilon?
Yeah. I mean, no, this epsilon is the same as the noise epsilon, but we will choose the noise epsilon to be the same as here.
And the players winning probably.
Yeah. So that will sort of balance the effect. So. Because this epsilon will also affect the completeness direction. So you want to balance.
Does the epsilon noise there has to be the same epsilon as 1 minus epsilon probability?
It doesn't have to be the same. I mean, so if I have here eta noise, then you would get here eta.
But you better not have.
But then how does epsilon enter?
So the issue is that if you add here too much noise, then there just won't be a good strategy, right? Because I mean, if I make everything, I mean, if you add half noise, then there just won't be a good strategy. So somehow, actually this epsilon has to be less than this epsilon. I mean, just somehow these noise vertices, they force you to lose with probability epsilon in some sense.
Sure.
Why do you need to choose t at random?
So this will be we still want some condition like that if we sort of look at the number of edges that leave S, it should be small, and to make sure that happens, we want to choose it at random. So yeah, you don't see it here, but you can. I mean, this is somewhat. This happens a lot in these metric embedding things that you're given some. So these probabilities, they give you some embedding between 0 and 1, and now you somehow want to find a good cut, and so you choose a random threshold. Okay, so this black thing indicates that that's all I'm talking about for the proof.
So I don't really see how you. So you have set this all up, but I don't see what your reduction is.
Sorry, the reduction.
You will now use the assumption.
Which assumption?
Players win with probability larger than.
Oh, this assumption is used just in this case that you can analyze using this assumption.
Why is that smaller than epsilon? That both of those, because you were assuming it basically.
No. If it's smaller than epsilon, then you get a contradiction. Is this right?
No. So here, here what we want, we have a good strategy for this unique game. And we want to say that implies there's a small non-expanding set.
Then,
oh, I see.
Then it's not going
Yeah.
to be.
Okay. So actually, this analysis shows something quite strong. Much stronger than kind of the. It sort of says that this epsilon is roughly the same as the expansion that you get. So if you sort of look at the value of the game, if it's 1 minus epsilon, then you will find a non-expanding set of size epsilon. And sort of if and only if so these two parameters are preserved up to some constant factor in this reduction. So the only thing is that somehow in this reduction you will get a set that is too large. And so if you now you can make it smaller by sort of some tricks, just subsampling, taking a random subset of S that has only size delta, and then of course the expansion will increase, but it can't increase that much. Yeah, so I can.
Here the claim is for every U for every T this happens. So why do you have to pick U at random?
So U picking at random, it also is related to this to the number of edges. Okay, so it's just some conclusion. So that's the summary for the talk. So we were sort of looking at these. We saw that all these important implications of the Unique Games Conjecture, and we sort of also wanted an implication of a refutation of the Unique Games Conjecture, or so actually there are sort of like lots of ways to think about this reduction. So for example, one way to think about it is.
Question. So the yes instances had volume about delta, and the no instances have volume like delta over epsilon. Is that right?
So what I said so far, yeah.
He said he has to subsample to get.
Oh, you can go back to delta, or
yeah. But then you will sort of. So now you have like a set that doesn't expand at all. It just has expansion epsilon. Now if you subsample, then its expansion will increase.
But not by as much as you cut that down.
Yes, right.
Right.
So you will still have somewhat set that doesn't expand a lot.
So the two volumes are really nearly the same.
Yeah.
So yeah, because before you said 10, and 10 is not whatever it is.
Right.
Right.
Yes.
What's epsilon?
So another way to think about this reduction is that somehow these implications, they sort of shifted the focus from these problems to unique games. And somehow if you want to understand these problems, then, or let's say if you want better algorithms for these problems, then we first have to find a better algorithm for this problem. And now this reduction sort of does the same thing, just by it says that if you want to have a better algorithm for these problems, then we first have to find a better algorithm for
and that's
small
so
cell
much
expansion.
easier to explain to people.
Yes, exactly. Yeah. So that's that's one of the reasons why. So now we don't have to. Now I don't have to show these slides with the referees and the players anymore.
So basic SDP may not be that easy to explain.
No, but I mean, small set expansion is so much easier to explain than unique games.
Okay, so
Then you don't have to explain that's not game theory.
Right. Okay. And okay, so some open questions. So what you?
All game theory.
Right. Okay. Some open questions. Okay. So of course it would be nice, maybe we don't want to break with the Unique Games Conjecture right now. So maybe we could still try to find other implications, other sort of reverse directions for
But
it.
of course, I mean, that one of the problems is you may have lost something there, right?
Yes. Right. Sure.
So.
Yes. It might be that this problem is easy and
It's
unique games is not easy. And that's true. I mean,
It doesn't look easy.
right.
Because you're looking at sets of linear size.
Mm-hmm.
It doesn't seem easy.
Right.
Yeah. And then another thing that you could try,
Yeah.
so this is a weaker. I mean, this is a weaker assumption than Unique Games Conjecture. So maybe you can show better hardness results using this assumption. Maybe for other problems where we currently don't know properly how to prove unique games results. And okay, another thing that I wanted to point out is this reduction is somewhat inefficient. Because if you look at the size of the unique game that you get after the reduction, so with our strategy, it really has to it has to look at all sets of size R, and decide which of the vertices to pick. So the unique game here has size. If the graph has size n, and then it has size n to the r, and r was like 1 over delta. So it's really a huge instance, and it's sort of the kind of blow up that you see, if you do parallel repetition, and
Which doesn't work.
yeah, right. I mean, so you can also, I mean, there's some similarities between this reduction and parallel repetition, and okay, and there you also see why it's sort of where we had to assume that the size of the set is roughly delta, because if delta is, if the set would be much smaller than constant, if for some reason then the smallest non-expanding set in the graph has size 1 over root n, then the reduction would take time n to the root n, which is not efficient anymore.
So where's this submitted?
Stock, I guess. Yeah.
So it's being decided on as we speak.
Right. And so I can maybe I can talk about it again here in Cambridge.
Just got an email saying it was accepted.
He's lying.
But you should know.
Or did you just send them an email not to accept it, right?
Oh,
I just saw this talk, and I don't know.
I think it would be nicer to the speaker. I think it was to tell him it's subjected so that he can enjoy this
We'll try different psychological games on you. So
The Baroque nature of the UGC is giving rise to a lot of Baroque ideas.
okay.